Okay, so to start off, I'm going to have you do example 8.2 as a bit of a refresher to see if you can draw Lewis structures for these four substances. Now notice it says that these are all isoelectronic. If you forget what that means they all have the same number of electrons. So you'll find that when you calculate your total number of valence electrons, they will be the same for all four of these molecules. So what I'd like you to do is pause the video right now, and as a bit of a warm-up, try and draw Lewis structures for all four of the compounds you see here. Okay, now that you've drawn the Lewis structures, you should have found that all four of these substances have 10 valence electrons. So when you go to draw your Lewis structures, all of them, notice, also only have two atoms. So that means when you go to draw these, at first you would make your connection, so 2, then you'd start filling in, so 4, 6, 8, 10, but we see that we run into an issue here because this oxygen has 8 electrons, but the nitrogen does not. So what we'll need to do is shift 1 and 2 of these pairs in so that we end up actually with a triple bond between these two. This one had a charge, so we should put that in brackets as well. So what we see here is that if I do my checks, I've used 10 total electrons, 2, 4, 6, 8, 10, and both atoms are surrounded by 8 electrons. Conveniently, when you do the other ones as well, since they're all just 2 atoms with the same number of electrons, what you will find is that for the same reasons, you're going to end up with 4 very similar Lewis structures. So we can draw the conclusion from that if we have isoelectronic species with the same number of atoms, we will ultimately end up with similar Lewis structures. Okay, so there are our Lewis structures. We've already done worksheet 1, so you don't need to recomplete that, but that's a little bit of a refresher on our Lewis structures. Now, all 4 of these are ones that follow the octet rule, and all of the ones from example 8.1 were ones that followed the octet rule. What we're going to be getting into in this next section are ones that do not follow the octet rule. Now notice this is from section 8.5, so we're going a little bit out of order here, but I think this part fits nicely after having just gone over our original Lewis structure lesson, okay? So our exceptions to the octet rule, there are kind of 2 options for our exceptions. Option 1 would be what we'll call reduced octets. So these are elements that are okay with less than 8 electrons. So in other words, they're not really surrounded by a true octet. So by calling it a reduced octet, it's not really an octet because it's not 8 anymore. But you need to know which 3 elements will typically form these reduced octets. So as we've already mentioned, this one we should already know. Hydrogen only needs a duet, so it only needs 2 electrons. But the 2 new ones are these 2 right here, beryllium and boron. So beryllium is okay with being surrounded by 4 electrons. Boron is satisfied with 6, so they don't actually try to get a full octet. They will stop when they get to 4 or 6, even if it's possible to get them 8. They will stop at 4 and 6. So if we look at our molecules here, H2 would give us 2 total electrons. BeCl2, if you do your math correctly for that one, for BeCl2, we're going to end up with 2 plus our 7 times 2, so that's going to give us 16 electrons total. And then for boron trichloride here, we're going to get 3 plus our 21 there, so that's going to give us 24 electrons. Okay, so now that we know our total number of electrons, when we go to draw our Lewis structures, we'll see that our H2 molecule is just going to look like this. They're each okay with 2 electrons from this bond right here, using our 2 total. If we look at our next one, Be would be our central atom because we only have 1 of them. Then we would connect each of our chlorines. Now remember that used up 4 of our 16 electrons, so then we would start filling the outer elements first. So we've used 2, 4 already, so 6, 8, 10. This would be 12, 14, 16. Now, if we look at our total here, we did indeed use 16 electrons, and if your inclination here would be to say, well, Miss Adams, if I flip those in there and make double bonds, I would be able to get beryllium to 8. While you are correct, because beryllium is a noted exception to the octet rule, it will stop this way. Basically, the chlorines are so much more electronegative that they will not want to share in double bonds, and beryllium will be satisfied with just these 4 surrounding electrons. Our final example is the BCl3, and similarly, we'll end up with our central atom being the boron, our chlorines around the outside here. That used up 6 of our 20. Let's go 10, 12, 14, 16, 18, 20, 22, 24. Again, we've used all 24 electrons, but even though we could technically make a double bond between one of these chlorines and boron, it will not. It will stay just like this. Boron is satisfied with 6 electrons instead of 8. So for these reduced octets, you need to memorize these 3 elements, because otherwise you're going to try to get to 8 like you would have by making double bonds between these two, in those two. Okay, so you need to remember that these will be okay with 2, 4, and 6. Therefore, we should not try to get those 8 electrons. So those are our exceptions that we'll call reduced octets. Now, if we move on to our other set of exceptions, these would be what we would call our expanded octets. So these are all elements that are okay with more than 8 electrons on the center. So I should say that these would only be central atoms. Okay, so these are not the only possible ones that you see here. These are just the examples we're going to draw. What's nice about these is you don't need to actually memorize these. What you'll find is that if you follow the process that we've done in our previous Lewis structure examples, if you follow the same process, you're going to end up realizing as you draw the Lewis structure that, oh, this is an expanded octet. But you don't actually need to memorize it, which is nice. So otherwise, our process is going to work the exact same way. So you will get your total number of valence electrons, make all your connections, fill the outer elements first, and often what you'll find is you have extra electrons, and they'll go on the center. The other case would be one where you would already have more than 4 things attached to the center. So these are not the only elements that will form these expanded octets, but they're ones that commonly will. Okay, the fancy name for these besides expanded octets are hypervalent compounds, where they have more than 8 electrons on the center, but that's one other name for them. Okay, so what I'd like you to do is take a minute, pause the video, and try to draw Lewis structures for these 4 using the process that we've already done. Okay, so pause the video now and try your best to draw Lewis structures for these 4 substances. Okay, so I filled in the totals there for our total number of electrons, so let's start with PF5. So for PF5, if we draw our Lewis structure, our phosphorus would be in the center. We're going to first make our connections to all 5 of those fluorines. And that already we can see is an exception to the octet rule, because this makes our central phosphorus here surrounded by 10 electrons instead of 8. But we're going to go with it and follow our rules, and we'll see that it just is an exception, but it still works the same way otherwise. So now that I've made all my connections, I'm going to start filling in those outer elements. We're going for a total of 40. So I already have 2, 4, 6, 8. This is 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So I've used all 40 electrons that were there, and we see that this is indeed an expanded octet because our central phosphorus there is surrounded by 10 electrons. But all of those outer fluorines do have 8 electrons and follow the octet rule. So now if we look at our next one, SF6, this is another one where we can see already it's going to be an expanded octet because I have 6 things attached to that central sulfur. So I'll have our sulfur in the center. We'll make our connections to all 6 of our fluorines. Again, that's going to give our central sulfur here more than 10 surrounding electrons. We see that this has 2, 4, 6, 8, 10, 12 electrons surrounding it. So it is an expansion. But if we then fill in our outer elements, we will see that, or our outer octets, we'll see that we will end up with using 48. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Sorry, that's a single bond. 42, 44, 46, 48. So there we are with our Lewis structures there. So those are ones where it's obvious to tell that we have a expanded octet because our central atom has more than 4 things connected to it. Now these remaining 2, here and here, these look like they should follow the octet rule, 4 things attached, 2 things attached, but we'll see that with the extra electrons that will not be the case. So if we look at ClF4, we'll first start by taking our chlorine and connecting all 4 of those fluorines to it. So far so good. It follows the octet rule right now. that would take 36 electrons. So I would have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we have 4 extra electrons. We already filled the outsides. So remember, if you had extras, they go on the central atom. So now that we'll see, our chlorine in the center is not actually surrounded by 8 electrons. It's actually surrounded, including those lone pairs, it is surrounded by 12 electrons. Okay, so we have an expanded octet there. And then for our final one, if we look back at our last one here, we'll see our xenon. This is one of the rare cases where noble gases are actually involved in bonding. So we would have used 4 there. Then we fill in our extra electrons, and what we'll see is that we have 6 extra electrons. So all 6 of those extra electrons will go on our central atom, again showing that we have an expanded octet here, because we'll see that our xenon is surrounded by, instead of 8, we have 10 electrons. Okay, so those are examples of our hypervalent or expanded octets. So again, what's nice about these is you do not need to memorize the expanded octets. You will just see that when you draw your Lewis structure, you're ending up with more than 8 electrons on the central atom. It only will apply to the central atom, and typically these elements have to be in the 3rd period or lower on the periodic table. So basically they need to be some of the larger elements. Okay, so the final section we're going to do in our video lesson today has to do with what are called radicals. Okay, so these are also exceptions to the octet rule, but for a different reason. Radicals are substances that have unpaired electrons. So in other words, they have an odd number. So if they have an odd number of electrons, that means that we won't be working in pairs. So one element will not be having or not be surrounded by 8 electrons. Okay, using a term from last chapter, remember that we could say these are paramagnetic, meaning we have unpaired electrons. Okay, and that means they could be affected by an electric field. These radicals are also extremely reactive because of that unpaired electron. So typically they will not stay that way for long. Okay, but if we do our 2 examples here, we'll see that for nitrogen monoxide, we're going to end up with 11 electrons, because 5 plus 6. And then for NO2, we're going to end up with 17 electrons, because 5 plus 12. So you're not wrong. I said previously, if you got an odd number, usually something was wrong. The rare case where that is not true are with our radicals. So we're going to follow the same rules we did with our other Lewis structures. We're just going to have to think a little bit carefully about where to put that unpaired electron. So for nitrogen monoxide, we're first just going to connect them like we've always done. Then you start filling the octets on the more electronegative element, which would be the oxygen. Excuse me. So we would go 2, 4, 6, 8, 10, 12. Okay, but remember we said we don't actually have 12 electrons. We only had 11, so we need to get rid of one of those. Now, I can shift a little bit to try and make nitrogen a little bit closer to 8, because our oxygen here has 8, our nitrogen only has 5, right? 2, 4 plus 1 is 5. So what we can do is shift one pair in here to make a double bond. That's still going to give our oxygen 8, 2, 4, 6, 8, and this is close. We've got 2, 4, 6, 7. So while this one follows the octet rule, this one does not. That one only has 7. So that would be extremely reactive because it's missing 1 electron on that nitrogen there. The other example was our nitrogen monoxide. So for nitrogen monoxide, NO2, it's going to look similar to start. Make our connections. That was 4. We have 17 to go. So we do 2, 4, 6, 8, 10, 12, 14, 16. Now we have an extra. Extras go on the center. So we're going to have just 1 lone electron on our nitrogen there. Once again, this does not give our nitrogen 8 or even close to 8. It only gives this 5 again. So we are going to need to make a double bond. Now, for now, we could make the double bond on either side. It does not matter at the moment. So I'll just take one of these pairs off and draw a double bond. That's still going to give this 8 electrons here. It's still going to give that oxygen 8 electrons, and that would now give our nitrogen at the center 7 electrons. Okay, so these are our radicals. They are rare, but occasionally this will happen. One thing to note about this, if you're reading ahead in the book, if you have read ahead to section believe it is, let me get the right number here, section 8.4, what we'll see is that this structure displays something called resonance. But we'll talk more about that in section 8.4. So if you want to look ahead a little bit in the textbook, if you go to section 8.4, you'll hear about how that displays something called resonance. But at this point, you should be able to do homework number 1. That is in the textbook. It's listed at the end of the notes packet. So if you look that over, it's essentially lots and lots of Lewis structures, so lots of practice. Okay, so your homework tonight would be homework 1.